floor is yours.
Thank you. I hope you can see my slides.
Yes, you're all set.
Okay, hi, I am Işıl Öz. I'm an assistant professor in Izmir Institute of Technology. And in the meantime, I'm an LibOS Foundation mentee, which is supported by ELISA. And my mentor is Elana Copperman. I first of all thank you, her and ELISA, to support me in this work and open very different ideas in my research. And before I talk about the concept which I introduced today, I want to introduce myself and my research group. I got my PhD from Boğaziçi University in Computer Engineering Department, and I worked as a postdoctoral researcher in Swedish Institute of Technology, and I joined as a faculty member to my department. And in our research group, our Parallel Systems Research Group, we are trying to optimize and work on the parallel computer systems. And specifically, we are trying to develop software which will run on multi-core systems and the GPU-based systems. And more importantly, we are trying to analyze the performance and the hardware reliability of that systems. And actually, the security part, which we are conducting in our analysis, was a kind of missing. And with this mentorship program, I hoped to introduce the security, the hardware security part in my research, in our research as well. And actually, it is going well. So I'm very happy to include this security, which is very important issue in the hardware system evaluation. And with combining the reliability and security, I think it will be a very good contribution to the safety. Okay, we are not targeting the satisfying the specific safety requirements, but we are a kind of supporting the safety of the target systems. Okay, today I will talk about the trusted execution, hardware trusted execution environments. Actually, as we are using the cloud resources more, the secure remote computation becomes much more important. And since we are porting our applications in the cloud resources, we want to make sure both the code and the data are secure. And actually, these hardware trusted execution environments are some solutions for this secure execution. And if we look at the software part, for example, the homomorphic encryption provides this secure execution as well, without the executing the target program in a decrypted data in encrypted data without decrypting it. But there are some performance issues about this approach. So normally the hardware is much more efficient in terms of performance. So these hardware trust execution environments are implemented. The T technology is implemented by different vendors. And the general idea is something like that. You are executing your execution program in an isolated environment, which is assisted by hardware, and in which you are trying to have a secure container, and you are a kind of eliminating the accesses to this execution. And this T technology actually aims to protect the execution, not the data at rest, not the data in transit, but the data in use. And this T technology is also different in terms of the size of the data and the code to be protected, because you don't need to protect all the application, including all the code and the data. You can just define a smaller trust computing base and trusted computing base, and it improves the performance because you don't need to execute the unsecure part. I mean, the parts of your execution that don't need to be secure. So as I mentioned, different vendors implemented these T in their processors. The Intel SGX, software guard extensions, the ARM trust zone, and the memory encryption technology are some implementations. And today in my talk, I will focus on the Intel SGX and the software top of this technology, this implementation. And okay, for the T technology, actually, it has to support the data confidentiality, first of all, because you don't want your data will be visible to other people, other parties. And of course, the data integrity and code integrity is a must for this kind of secure execution. So you want to make sure the code that's being executed is the code you intended, and the data in which this application is processing should also be the data you want to process. And other than these more important concepts, you might also want to have code confidentiality. For example, if you want to protect your machine learning algorithm, the T technology also provides that. And another one it is providing is the authenticated launch. Okay, you don't want to be accessed or by other parties, but even you don't want to launch your execution without your requirement, without your wish. Okay, and this technology also provides that. And other thing it provides is the programmability. Okay, as I mentioned before, in your application, there might be some parts that you don't want to protect, and this technology allows you to kind of configure your program according to this. And there might be some third-party tools, third-party libraries, for example, you can include in your program, and you also need to do this kind of stuff, and this is also something you can have. And the recoverability, for example, you can assume your code is a kind of compromised, but you can roll back up to some points and you can re-execute your code. That's also possible. And more importantly, actually, the attestability. Okay, you are porting. Okay, I will mention about the details, but you are a kind of executing. This is the aim. Your code and your data, and storing your data somewhere which is secure. But how you can make sure, okay, this application is being performed inside the secure memory space. So this technology also provides this attestability, software attestability feature. And in general, overall, the T technology, the trusted execution environment technologies in general, provides hardware-based isolations. And as I mentioned at the beginning, it also, we can see it also as support point for the safety. Okay, so we are not talking about the strict safety requirements, but the security is an important part of the safety. Okay, if your application or data is accessed by some third parties which are not allowed, it's not good for the safety as well. As I mentioned, today I will focus on the Intel Software Guard Extensions, SGX implementation of the trusted execution environment. And here is the idea is you are defining if you have the processors supporting SGX, you have some isolated memory regions, which are called as the enclaves. And you can have these memory regions for code and the data. Normally, you are using your physical RAM for ordinary physical RAM for storing both the code and the data of your application. And in here, we have some processor reserved memory spaces, actually, the PRM spaces. And they are non-addressable memory pages, and they are only accessed by the CPU. And the CPU actually, CPU with this technology actually protects your data in some encrypted format. And it's not allowed to access these memory pages other than the code and the data inside these enclaves. And by using that, you are achieving the trusted execution inside these enclaves. Actually, if you want to execute your code inside or in this technology, in these memory regions, which are on the processors supporting this technology, you you need to have three main steps. And first of all, you are loading your application in your untrusted part of your memory. So actually you are launching your application normally. So because you are not worrying about that part, it should not be secure. And inside this untrusted part, you are creating your enclave. And so you are telling, this is the code and the data portion, which I want to port into that region. And you are a kind of porting some part of the code, for example, by calling the specific function and by a kind of copying the part of the data you are working on. And after, and in order to do that, you need to call some SGX instructions, which are provided as part of the SGX technology. And after that, you can just start the execution of the vulnerable, maybe I can tell, the part of your execution. And both the code and the data processing these processed by that part of code will not be visible to the other parties, including the operating system, the virtual machine, and the other parts in your system, because we are a kind of assuming the operating system can be also compromised and can include malicious code. So we don't want to allow the operating system can also or is able to see the code and the data we are processing. And as I mentioned before, the third and very important feature of the trust execution is the attestation. And actually during the execution, by calling some SGX instructions, you can create some hash values which are used to verify, this execution is protected by this T technology. So you are a kind of verifying the identity of the enclave, This execution occurs inside the enclave. And as I mentioned, for these three steps, you are using or you need to use the specific SGX instructions, which are coming with this SGX technology. And we have some SGX instructions, and they are a kind of providing the interface between the hardware and the software. And as I mentioned, we are not trusting the operating system as well. So in order to support the execution on the enclaves, there might be some effort to develop some LibOS projects. And we have some open source LibOS projects. They are mainly actually implementing the system calls and the other stuff. So you can see them as the and they are also defining themselves like that, lightweight operating system. Okay, and actually the Intel itself sorts these projects in its web page. So, and we had in my at the beginning of my internship phase, we had looked at the source codes of these projects, and one is the Grameen, maybe the most widely used one. And as I mentioned, it is a lightweight. It presents a lightweight library operating system, and instead of running a complete operating system, it just implements some of the system calls and provides the execution of unmodified applications. Okay, you have your application, and without requiring the modifications in different parts of your application, you can, I mean, it has some system calls and some low-level library calls, this kind of stuff. It just provides the execution inside the enclave, secure execution. And Oculum is another open source project, and in here it's similar to Grameen, and they are claiming they are multi-process. They are providing multi-process library. And the difference between them, the Oculum is implemented in Rust programming language. And as you have seen in our previous presentations, the Rust can be seen as a memory safe language. So the Oculum developers claim that because of this feature, the Oculum development and the execution is much safer, maybe I can tell in that way. And there is also Intel SGX and the Linux kernel library, which is also a research effort. And finally, and actually the one we kind of selected for contribution is the Mystikos. And Mystikos is also similar to other projects, but I want to give details of that since it's our focus. It actually provides runtime as the ones I had already mentioned. So a kind of library operating system and a set of tools, which I will briefly mention, which actually makes the execution of or porting the application into the enclave. So there are some steps we will see how we will port this application into the enclave. So the Mystikos has some tools, small tools, to be able to perform these steps. And these tools, as I mentioned, provides the running the applications in T environments. Yes, and it's open source in GitHub, and actually it is currently only supports Intel SGX, but they are claiming to extend it for the other T technologies as well. And if we look at the general goals of the Mystikos, it mainly enables the protection of the application code and the data while it is in the protected memory, which the T technology enables us. And again, as I mentioned, okay, you want to port some part of your application, some part of your code and the data into the trusted computing base, which will be executed, processed securely. So these Mystikos also tries to helps the developers to be able to perform this operation. And this is not implemented. I mean, the only T architecture is the SGX, but the one of the main goals is something like that. Okay, you are, for example, you have used the specific version, I mean, specific architecture, which is the SGX right now. And by almost no effort, you will be able to retarget to other architectures. This is also one of the goals. And if you look at the a kind of low-level architecture of the Mystikos, it's not so complicated. Okay, you have the application in the top and the SGX sub-enabled architecture in the bottom. And in your applications, you have some POSIX calls, and these Mystikos architecture provides a C runtime based on muscle, but actually it also supports the glibc GNU-C library. So these runtime functions are calling the system calls, and similar to the other open source projects, it provides these lightweight LibOS, some system calls, and so actually which makes the kernel. So you can use, or you can use these system calls inside your application whenever it is being executed inside the enclave. And there are some work going on here. So there are some implemented syscalls, and some of them are not implemented yet. And the other part of the architecture is a T-call, which is a kind of kernel target interface, okay? Because, okay, they have the kernel and they have the hardware. So there must be a kind of interface between these two layers. And actually the Mystikos, okay, I had talked about the Mystikos right now supports the only SGX. Okay, they are targeting the other T technologies as well. And it also has the Linux target. Okay, if you have the SGX enabled architecture, the processor, you can execute your code by using the Mystikos on this SGX enabled processor by porting your code and data into the enclave memory. But if you want to just to verify, just a kind of simulate your execution, they also provide the Linux target, and in which you can, of course, not execute your code in a secure way, but you will be able to see how it works. And here also you can see the OE. Actually, there are some, there should be some SDKs, also a kind of interface between a kind of, it can be seen as a kind of driver. So in order to utilize the features provided by the SGX, the Open Enclave, this OE Open Enclave SDK is used by the Mystikos. And there are also other SDKs to provide these SGX instructions to the kernel functions, the system calls in these implementation, in these projects. And if we move into the high level of the Mystikos, how one application will be a kind of ported to the enclave usage by using the Mystikos. Okay, you are developing your application firstly, and of course you are creating, okay, this kind of this part of my application will be executed on the secure memory inside the enclave, and the other part will be unsecure. Then as a step one, and as a step two, you will create an application directory simply, or you can generate a Docker file as a container as well. And actually there is a tool inside the Mystikos. I had mentioned about the tools provided by the Mystikos, and one tool is to create this application directory. And after that, you will generate the root file system, and you can do it as the CPIO archive or the X2 image. And after that, you are ready to run your code, to run your application with the SGX. And as I mentioned, it can be the SGX target or the Linux target, but of course, our main aim is to be able to execute our code on the SGX. And there is also one different tools for the run SGX or the run Linux options. And optionally, okay, you are ready to ship, so you you prepared a kind of your application ready to be executed on the SGX enabled processor. You can ship, because at the beginning our aim is a kind of to be able to execute our code on the cloud resources securely. So you can just package and sign if you want to be able to run on the cloud resources. Okay, this, and as I mentioned, for each step other than step one, because you are developing your application at that stage, the Mystikos provides small tools to be able to have the output of each step. Okay, what I'm doing in this Mystikos project, actually I'm in the middle of my mentorship phase. And as the maintainers suggested me, I'm trying to work on the debuggability inside the Mystikos. And specifically, I'm trying to have some interactive shell support to be able to understand what is going on inside my execution, inside the Mystikos execution, actually. And for example, we can run tracing and profiling tools, which are mentioned during the sessions we have today, like the strace, the vagrant, the pin tool, this kind of stuff. And we can analyze the CPU usage, or we can analyze the memory leaks, these kind of, okay, if we have something wrong in the execution of these Mystikos, what is wrong? We are trying to understand this. And actually, I believe it is very helpful to be able to understand the internals of this project. Okay, this is a new project for me. Although I have a theoretical background or the operating system and okay, some theory and practice in the computer architecture, it is very new for me to be able to contribute on an open source project. So it will be a very good starting point for me, I believe. And what are the next steps? Actually, okay, after having some more work on the Mystikos, more implementation, actually, I have already created a pull request and commented on some issues on the GitHub, but working about this debuggability and having some concrete, I want to continue with much more maybe important or focused work like the additional system calls. As I mentioned, the system calls are not fully implemented as part of the Mystikos. I want to also contribute that part. And after that, actually, since my main research interest is the GPU systems, I also want to look at the effects or the ways how to communicate between the trusted CPU and untrusted GPU memory. Because, okay, we have the GPU itself, and as far as I know, the memory of the GPUs do not have this kind of T technology, but we can have an application which has parts that's to be executed on the trusted enclaves, inside the trusted enclaves, but on the other hand, we have some untrusted GPU parts. So how to communicate this, something I want to look into. And actually, I have already submitted a national research project, and I want to extend the work for the safety critical embedded CPU GPU systems. Okay, hopefully I will have some hands-on experience on the CPU execution and how it can be extended to be able to support the safety again for these embedded CPU GPU systems. This is something I want to look at. Okay, thank you. I think that's all from my side. If you have any questions, I can take.
Işıl, check in the chat. There's
okay.
Okay.
I think there's one question. Is an SGX-based enclave also protected from an availability perspective? For example, could the surrounding untrusted process destroy an enclave it has created, started before, or could this enclave only actively stop, destroy itself? I'm not sure about it, but as far as I know, yes, the enclave is a kind of responsible for itself only. Is that the question? Thank you. So again, I want to thank the Linux Foundation and the ELISA to support me in this work. I am very happy to be part of this work and introduce myself in this community and hopefully support my future research.